Okay. And we have lecture number 4 on critical systems and real physical critical systems and three-dimensional.
Well. Okay, just 1 second. I need to. I had one sheet of paper somewhere. Okay. Okay, this is what I want. Okay, so this is some of the stuff that we discussed yesterday. So if we have identical scalars in a 3-dimensional CFT, the 4-point function looks like this. So it's some prefactor and then some function of u and v, where u and v are conformally invariant cross ratios. And this 4-point function, if the scalars are identical, satisfies a crossing equation, which is v to the delta phi g of uv minus u to the delta phi g of vu equals 0. And if we further use the conformal block decomposition of the 4-point function, we can rewrite this crossing equation as a sum over primaries, conformal primaries appearing in the phi times phi OPE. There's some OPE coefficient squared times some function of u and v that depends on delta and L. Maybe I should say for identical scalars, this function doesn't depend on delta phi. But if the scalars are not identical, then it would also depend on delta phi. It would depend on differences of the scaling dimensions of the external operators. In any case, this is determined by group theory. What's not determined by group theory is what operators appear in the sum and with what coefficients. But that's still pretty good because we can still rule out various possible spectra for the CFT. Here I rewrote that equation by isolating the identity operator and assuming that f phi identity is equal to 1. That's just a normalization condition for phi. And here this is a sum over all the other operators, all the other conformal primaries, not the identity operator. And then if we can find a functional such that when acting, a linear functional, such that when acting on f00 we get 1, that's just a normalization condition for the functional. And if the functional acting on scalar operators of dimension delta bigger than some value, delta star, is positive. And if the functional acting on the f's corresponding to all other operators of spin bigger than 0 is positive, where the dimension satisfies the unitarity bound. If we can find such a functional, then if we apply this functional to this equation using the fact that this is positive in the unitary theory, we see that this equation cannot be obeyed. So that implies that the lowest dimension scalar appearing in the phi times phi OP has dimension smaller than delta star. So this way we find an upper bound on the scaling dimension, and then we can optimize over alpha so that we find the best bound. And this is a sort of plot that one gets. And the important features is that if it starts at the free theory here, and it goes up and there's a kink precisely where the 3D Ising model is, and then it does other things. And I explained last time that if we do something a little more complicated, we don't just look at a single, the 4-point function of a single operator, but a mixed correlator system, then we find an allowed island around this point. It's an interesting question whether the island can actually shrink to 0 size, but I think people believe that's true. Okay. So I want to make some comments about this method. And then talk about other examples. So note, if we know one of the OP coefficients, one or more, the OP coefficients, say f phi phi O tilde for some operator O tilde, then we can improve the bounds in the following way. So I'm going to rewrite this equation by isolating not just the identity, the contribution from the identity, but also the contribution from O tilde. So suppose O tilde has dimension delta tilde and spin L tilde. So f 0, 0 plus f delta tilde L tilde plus some, sorry, forgot to write the OP coefficient that we know, phi phi O tilde squared, plus sum of over all the other operators, f phi phi O squared, f delta L, where delta and L are the scaling dimension and the spin of this operator O, is equal to 0. And then we can, in order to exclude assumptions about the spectrum, so then in order to exclude a possible spectrum, find a linear function alpha such that the following, find alpha, well, with the same conditions as here, except that instead of alpha acting on the identity operator being normalized to 1, so where instead of this, we use the normalization condition alpha acting on this combination is equal to 1. F 0, 0 plus f phi phi O tilde squared f delta L, delta tilde L tilde is equal to 1. Yeah. I want one of the terms in the sum to be strictly bigger than 0, not greater or equal. If everybody is greater or equal than 0, then that's not good enough. The fact that it's 1, it doesn't matter. It could be any number, but it should be strictly bigger than 0. Yes. Okay. So this is one comment that one can actually improve these bounds if we know the values of some of the OP coefficients. Of course, in the 3D Ising model, we don't. Well, using the Bootstrap, maybe we can find them, but a priori, there's no calculation that gives them. And another thing that I want to say, well, there are theories in which we can calculate some of the OP coefficients, and I'll explain that, hopefully, if I have time, in some supersymmetric theories. One can actually compute some OP coefficients. And in those cases, one can actually improve this method in this way.
Typically, you can measure like 2-point function.
Right, so this would be a 3-point function.
Yeah.
Yeah, presumably from a simulation that would also be possible. I think for the Ising model now we know some of the OP coefficients thanks to the Bootstrap. Okay, and I want to say another thing about the OP coefficients. Then we can find bounds if we don't know the OP coefficients. We can find bounds on OP coefficients using a slight variation of that method, and it's as follows. Let's just suppose we want to find a bound on this OP coefficient f phi phi O tilde. So let's just write that term first, f phi phi O tilde squared f delta tilde L tilde, and let's just put everybody else on the right hand side, minus f 0, 0 minus sum over the other operators, primaries, f phi phi O squared f delta L. So this equation is true. Okay, and now the idea is, if I was better at using these boards, I think that would be good, but unfortunately I'm not. So I'm just going to write it here. Find alpha such that alpha acting on f delta tilde L tilde is equal to 1. So it's normalized a little differently from there. And alpha on f delta L is bigger than 0 for all the other O's, not the identity, or the operator whose OB coefficient we want to find a bound on. So if we can find an alpha that satisfies these two conditions, then if we apply alpha to this equation, alpha acting on this f is equal to 1 by normalization. Alpha acting on this is positive, so this whole term here, because of the minus sign, is less than 0. So this implies that f phi O squared is less than minus alpha applied to the identity. So if we find an alpha with these conditions, satisfying these conditions, then we can just evaluate alpha on the contribution from the identity, and we find an upper bound on the OB coefficient squared. So then optimize over alpha and find the best bound. Okay. So that's another thing one can use this method for. And as I said before, in some superconformal field theories, one can actually calculate exactly some of the OB coefficients. Okay. Other questions about this? So then I want to explain a couple of generalizations. Yes?
Is that O or O tilde?
O tilde, O tilde. I'm sorry. Do I have O tilde? Yeah, I have O tilde there. Yeah. Yes?
So you practice how to do like the isolated O's because O's that
That's true. This thing would work regardless of whether O tilde is isolated or not. You still get a bound. It's possible to also get, so this is, for using this way of doing it, you get an upper bound. It's also possible, if there's a gap above this operator O tilde, then it's also possible to get a lower bound on this OB coefficient. So I think, what's that? Yeah, you have to know the gap. So for example, in supersymmetric theories, if there are some representations that are protected and they're completely isolated, sometimes they're completely isolated from the continuum of representations. And for those OB coefficients, you can find upper and lower bounds. Okay, so some generalizations. And I want to make a connection with what I talked about in the first. Is there more chalk? Yeah, okay, here. In the first lecture, so the first generalization is for CFTs with ON flavor symmetry and a scalar phi I, scalar primary phi I, where I goes from 1 to n, and the vector representation of ON. So this way we could make contact with these critical ON models. So what's different in that case? Well, we look at the 4-point function of these operators, so phi I, phi j, phi k, phi l. where the indices go from 1 to n. And of course, the 4-point function doesn't vanish only if these indices are contracted so that we have a singlet under the flavor symmetry. There are several ways of contracting these indices. And I'm going to write it like this. So delta ij delta kl times gs of u and v plus delta il delta jk minus delta il delta ik delta jl ga of u and v plus delta ik delta jl plus delta il delta jk minus 2 over n delta ij delta kl gt of u and v. And now I should explain why I did this. The idea is that when we take this OPE, so let's just take this OPE and that OPE and expand this 4-point function in conformal blocks. If we take this first OPE, there's some operators O that can appear in this OPE. These operators, in general, transform under ON. How can they transform under ON? Well, they can transform in any irreducible component of this product of two vector representations. So O can be an ON singlet. I'll call that S. On ON, so in the product of two vector representations, we get a singlet. If we contract the indices, we can get an antisymmetric tensor or a traceless symmetric tensor. So ON singlet, ON antisymmetric tensor, I'll call that A, and symmetric traceless, and I'll call that T. So then the way I wrote these this 4-point function is such that when we expand this GS, GA, and GT in conformal blocks, the only operators that contribute here would be the ones that are singlets under ON. Here there would be the ones that are antisymmetric tensors, and here would be the ones that are symmetric traceless tensors. You can check, for instance, that this structure here is antisymmetric under interchanging I and J. So it's just antisymmetric tensors that contribute when we take this OP. This one is symmetric under interchanging I and J, and it's also traceless if we contract I with, if we set J equal to I and sum over them, we get 0 because of this thing here. So this corresponds to symmetric traceless tensors. Okay? This is slightly more complicated, but this is sort of how theories with global symmetries are going to be studied. So then, even before we expand in conformal blocks, we can still write down the crossing equations. So crossing, meaning interchanging 1 and 3. So previously, if we had only one operator, crossing just relates G of uv to G of vu. In this case, we have three functions, GS, GA, and GT. So crossing will mix together GS, GA, and GT. So we have, and we get three crossing equations. Anyway, and then one can expand in conformal blocks, GS, GA, and GT, and use a similar method. Find a functional so that we exclude some possible spectra. And I'm not going to go over that in detail again, but I'll just show you the plot. So we can find an upper bound on delta S, which is the dimension of the lowest ON singlet operator that appears in the OPE of phi I and phi j. And the bound looks like this. So this point here is 1/2 2. This point here is 1/2 1. And then something like that. So I'm plotting the bounds for various values of n. And so these are upper bounds. Okay. So this is as a function of the dimension of phi I. So this was done by Coase, Poland, and Simmons-Duffin. Okay. And this would be, for instance, for n equal 1. This is like the Ising case. N equal 2, n equal 3, and so on. And you can do it to at the very large n. The bound just goes is very steep here, and then it goes like that. Okay. So, as you might expect, these kinks are exactly where the critical ON vector models are supposed to be. Yes.
Is it harder to do large n numerically, or is it
No.
the same for any?
No, it's the same for any n. So the way n appears, it appears in the crossing equations as a parameter, and the reason why it appears there is because it appears in this structure for symmetric traceless tensors. This is the only place where n appears.
So can we take n to infinity first before doing the numerics?
I'm not 100% sure. Possibly, yeah, I don't see why not. And then presumably you'll just start here. Right? So if you recall, okay, so let me just explain why this corresponds to the critical ON models. So if you recall, the action was something like this, some kinetic term, some mass term that we tune. So we tune this in order to reach the critical point, and some quartic coupling, phi I, quantity squared. And at large n, this theory is solvable. Delta phi I approaches 1/2. It's very much like a free theory as far as these phi i's go. The only difference between this and a free theory is that this ON singlet, the operator phi I, its dimension goes to 2 instead of 1. In a free theory, it would be 1. So you can see very nicely that as n goes up, this kink approaches, on the y-axis, it approaches 2. And then if in this case one looks at mixed correlators, again, one can find islands, but the islands aren't as small as for the Ising model. Yes?
Why is it only those the polar models? Could be there are other theories also contain such as scalar fields, vector.
Sorry, again?
Could there be another theory
That has ON symmetry?
Yeah, big model.
Yeah, there are probably many theories with ON symmetry. But the idea, I mean, you know, there are also many theories with scalar operators. So you could ask the same thing about the Ising case. Like, why is it that it's this theory that we're seeing? Well, probably in some sense it's like the simplest theory. I don't have a good explanation why these are the theories. It's like the most minimal theory with this amount of this symmetry. Right. So if you think that there aren't that many CFTs because of universality, then maybe that would be an explanation. as far as the numerics go, it's not. Right. Yeah. By the way, one can actually continue these things. So the scaling, the space-time dimension also appears as a parameter in the expressions for conformal blocks, and one can continue this across dimensions. And one can check that this kink for the Ising model interpolates between the 2D Ising model in 2D and the free theory in 4D. These ones also go to a free theory in 4D. I think they disappear at some point between 2D and 3D. Yeah?
So we mentioned that for water or magnets, the
Yeah.
kinks is
Yeah.
realized. Could you make an example for higher end or higher end determination?
Oh, I'm not going to remember the specific materials, but so the Ising case is for uniaxial magnets where the spins can be oriented and preferentially along one direction. N equal 2 would be relevant for XY magnets where the spins can be oriented somewhere in a plane, anywhere in a plane, and the N equal 3 case would be relevant for Heisenberg magnets where the spins can be oriented anywhere in 3 dimensions. For higher values of N, I'm not really sure. But it's interesting to study these theories especially because at large N they're solvable. Okay. Okay, so this is another case where there's a kink, just like in the Ising model, and I wanted to show you another one that's a little more involved, and I just want to give you a feel for how much more involved it is. So the second generalization would be to external operators with spin. And I'll just do one example. So example is fermionic operators. We'll just call them psi. And they have a spinor index, alpha, goes from 1 to 2. And I'm going to look at theories like this also with ON global symmetry. I'm going to have n flavors of these. So I can just put an index I, where I goes from 1 to n. And alpha goes from 1 to 2. So just a spinor index in 3 dimensions. And I can take these operators to be real, so Majorana. And they would transform in the vector representation of ON. Okay? Of course, these are 2 ingredients here. One of them is that we no longer have scalars, we have spinors, and we no longer have just one scalar, we have n of them. So it's good to just take them one at a time. So first, let's just do one fermion. So you can look at the 4-point function, psi alpha, psi beta, psi gamma, psi delta. And this can be expanded in conformal blocks just like a scalar 4-point function. The difference now is that we have to keep track of these spinor indices. So 1 over x12 to the 2 delta psi, x34 to the 2 delta psi, times some function of u and v, but also multiplied by some extra function of position that also depends on these spinor indices. So there are several ways of building conformally invariant structures, and in this case there's 5 of them. So I goes from 1 to 5, and T, I'm just going to call these structures alpha, beta, T alpha, beta, gamma, delta with the index I. They depend on the x's times functions gi of u and v. And these functions gi of u and v. Okay, so far this is what the 4-point function looks like. You can think of these t's as various ways of contracting these spinor indices. Maybe multiply them by coordinates as well. Okay. The fact that there's 5 of them assumes parity. So this assumes parity. If we don't have parity, without parity, I would go from 1 to 16. So you can see that even for the simpler generalization of operators of scalars, like fermions, even for fermions in 3D, it easily can get out of control because there will be lots of structures. Yeah.
Higher dimensions is the number of tensor structures bounded, or is it write all of them down?
Yeah. It's the 4-point structures. Yeah, the number is bounded, even for operators with higher spin. Yeah. Okay. And now each GI can be decomposed, expanded in conformal blocks. These are different conformal blocks than the conformal blocks for scalars. So how many conformal blocks are there? Well, we can try to think about it. So conformal blocks correspond to this OBE decomposition. So we should try to understand what this OBE decomposition could look like. So what kind of operators can appear? And so for that, we should look at the 3-point function, psi alpha, psi beta, times some operator of dimension delta, spin L. So it has spacetime L spacetime indices. It's a traceless symmetric tensor. And in the scalar case, this was just proportional to the OBE coefficient times some function of position, right? But when we have spinors instead of scalars, they're actually the same operator can appear with different OBE coefficients. So the way this looks is that it looks like this: lambda psi O A. So each operator has different OBE coefficients that they differ in the way we contract these indices, alpha, beta, and these mu's, and also with potentially with functions of position. So it looks like this: R alpha beta mu1 through mu L. It depends on A, so they're different 3-point structures. This also depends on X times some function of position. Well, I guess like if I say that this depends on X, I can just leave it like that. So one other difference is that they're different. Each operator has different OBE coefficients. And it just so happens that in this case, so A goes from 1 to 4, 1, 2, 3, 4. These are parity even. So a parity even operator O only has OBE coefficients with indices 1 or 2, and these are parity odd. There's 3-point structures for parity odd operators. And then these functions gi of u and v can be written as a sum over a and b. Lambda psi O A, lambda psi O B times G delta L and he has three indices, I, A, and B. And this is a function of U and V. So what's complicated in this case is that in order to figure out what the conformal blocks are, so these are the conformal blocks. These are conformal blocks. In order to figure out the conformal blocks, you have to keep track both of the 4-point structures and the 3-point structures. So you can imagine that even computing the conformal blocks in this case is not that easy. Okay? Yeah. Yes?
Sorry, just a technical question. So that's object T alpha beta gamma delta.
Yeah.
The conformal fixes there are taken care of by correct?
Not necessarily. You could have x's sandwich in between, multiplied by gamma matrices. Right. So you can, yeah. So you can have, for instance, you can have things like x1 minus x2 mu multiplied by gamma mu alpha beta. Divided, yeah. You should not scale with distance. Divided by absolute value of x1, 2. But of course, only very specific combinations are conformally invariant.
It's like a sweeter analog of that I
that would be for the 2-point function of the spinners. Yeah. Okay. So, this is a bit complicated. Maybe I shouldn't explain it in a lot of detail. One can compute these conformal blocks. So these can be computed. They're just determined by group theory, so they can, of course, be computed. They can also be related to the scalar conformal blocks by acting with some derivative operators on the scalar conformal blocks. One can figure out what these blocks are. So, in general, if you want conformal blocks for operators with spin, it's possible to get some of them by acting with some derivative operators on scalar blocks, but you may not be able to get all of them that way. You might need some other blocks from which, there's a set of what's called seed blocks from them. So it's a set of conformal blocks that you have to, for operators with various spins, that you actually have to compute. And then from those, you can act with certain differential operators to get conformal blocks for general operators with spin. Anyway, this gets very complicated. So this is the conformal block decomposition. Crossing, what does crossing do? Well, mixes together the GIs. And one can choose these TIs, these 4-point structures, such that they have nice transformation properties under crossing. So TI, when 1 is interchanged with 3, is plus or minus TI. I think out of the 5, you can take 2 to be even and 3 to be odd. And then if you define Fi AB plus minus is V to the delta psi times GAB, the conformal block, times GABI of UV plus minus U to the delta psi GAB I of VU. So this is the analog of this F function, which was G of UV minus G of VU. One can write down the crossing equation in terms of these functions. And the crossing equation, I'm just going to write it schematically just so that you see what it looks like. And then I'll tell you what one can find using this. Okay, so the crossing equation becomes something like this: sum over I, and then sum over parity even operators with even spin, and sum over A and B, lambda, maybe I can write it like this: lambda 1, lambda 2. So these are the OP coefficients for operators with even spin, times some matrix like this: F11, F12, F21, F22. These are the AB indices of F. Of course, everybody carries an index I. I'm not going to write that. Times lambda 1, lambda 2, plus the sum over operators with parity odd operators with even spin. So if I were to be more specific about the conventions, you'd see that it's just one of these OP coefficients that contributes, so it would be just lambda 3 squared times F33 plus sum over parity odd operators with odd spin, lambda 4 squared F44 equals 0. Anyway, just to give you an idea of how complicated this is. Okay, and then you can just try to, find a function alpha that when applied to these f's is positive. The new ingredient is that when there's a matrix there, and the condition that you want to impose is that alpha, when applied to that matrix, gives a positive semi-definite matrix. So that generalizes the condition that alpha acting on F is positive. Okay, but that can still be reduced to a semi-definite programming problem. 3 is odd. 3 and 4 are odd. 1 and 2 are even. Oh, the spin is even. Oh, sorry. The upper index on the operators is the parity. What's even or odd is the spin. Because they have different spin. So if you look at this 3-point function in more detail, you'll see that the thing that has the index A equal to 3 is non-zero only for even spin operators O, and the other one is non-zero only for odd spin operators O. Yeah. Anyway. So let me describe what one gets if we further assume that there's an ON flavor symmetry. So let's just look at CFTs with these operators psi alpha I. Why am I talking about theories with fermions and ON global symmetry? What do I want to find? I mentioned some models at on Friday with fermions that had ON global symmetry. So the Grosne-Uyakawa models, right? So good. So let me just so in these theories, if we take this OPE psi alpha j, we can have these intermediate operators O that can transform in as ON singlets S anti-symmetric tensors A, or symmetric traceless tensors. We'll just call that T. And of course you have to try several plots or think about what you might obtain if you think about if you try to find bounds on the scaling dimensions of operators in various symmetry channels. So the operators can transform under ON in those representations, or they can also be parity even or parity odd. So here is the most interesting plot, which is a bound, so upper bound on lowest dimension, parity odd operator in a traceless symmetric representation as a function of delta psi. Delta psi I. And it starts at 1, 2. Free fermion in 3 dimensions has dimension 1. In a theory of free fermions, we can construct an operator like this by taking a product of 2 fermions psi I psi j, and that would have dimension 2. And the bounds start here, and they look like this. So this is for n equal 2. For n equal 3, it looks like that. For n equal 4, it looks like that. For n equal 5, it looks like that. For n equal 6, it looks like that, and so on. So there's like a family of kinks that are here. And asymptotically at large n, this matches with a large n prediction from the Gross-Navuyu-Kawa models. So just to remind you, these Gross-Navuyu-Kawa models are, the Lagrangian is this, so psi I, plus there's a scalar, d mu phi squared. There's a mass term for the scalar that we tune. There's a quartic coupling. And there's a Yukawa coupling. That's why they're called Gross-Navuyu-Kawa. And the operator that I'm talking about is, so this operator is psi I, psi j. Symmetrized and with the traces removed. Okay? One reason why, you see a feature if you look at precisely this sector as opposed to other sectors. For example, you could have tried the parity odd singlet sector, where the operator, the lowest dimension operator is this phi. But what happens in that sector is that phi has a lower dimension in the Gross-Navuyu-Kawa model than in theory of free fermions. So in that case, what you find, if you don't impose any other assumptions, you just find a bound like that starts at the free theory, and the Gross-Navuyu-Kawa models are somewhere over here, deep in the allowed region. In this particular sector, one can actually, the dimensions, the scaling dimensions of the operators in this sector are larger in the Gross-Navuyu-Kawa model than in the free theory, and one can actually find these kinks. Of course, one can do more complicated things, but this is I just wanted to show you the kinks that are similar to the kinks in the Ising model, for the Ising model. Okay? Other questions about this? Yes?
Why there is no n equal 1?
Sorry?
Why there is no n?
Because this is the symmetric traceless representation, and that doesn't exist when n equals 1. The only representation would be the singlet.
This line, like the left line, so it's the same for all n? The one from which they break out.
Yeah, it's the same. It's the same, yeah.
Not like the theory bound.
It would be the n equal 2 bound. Well, psi squared is an irrelevant operator, so you'd have to think about having a UV fixed point. A better way of thinking about it would be, I mean, you could think about it like that, close to 2 dimensions, when this is slightly irrelevant. But a better way of thinking about it, I mean, it's just the same fixed point. You just add a scalar, and you flow from the UV of n fermions, n1 scalar, you flow to this interacting theory. And from it, you can flow to the theory of free fermions by just giving a mass to the scalar. And you integrate it out, and you have free fermions. What's that? What is it? At large n, the scaling dimension of phi is 1. What is the scaling dimension of phi? I believe it's smaller than 1. Yeah. Yeah, it's smaller than 1 because what happens is that when n is equal to 1, if you just have n equal 1, it's believed that the IR fixed point has n equal 1 supersymmetry. So then there's n equal 1 multiplet. And the scalar is the bottom component of the multiplet. And it would have, the scalar would have dimension equal to the dimension of the fermion minus a half. And the fermion would have dimension approximately 1, maybe a little bigger than 1. So then the scalar would have dimension a little bigger than a half, such that it's less by 0.5 from the fermion. And right, phi and psi I are the same operator. They're not different operators. Because another way of saying it is that the equation of motion for phi relates psi I to something in terms of phi. So you should only think about, I mean, thinking about this operator as phi or psi I is probably not very good. I mean, this can be made precise at large n, but at finite n, it's just a mixture of these. That's the operator with a well-defined scaling dimension. Okay. So then I wanted to show you another example with supersymmetry. So superconformal field theories in 3 dimensions are invariant under a superalgebra, which is OSP and 4. This contains as a subalgebra SON and SO3, 2. That's the same thing as SP4. That's the reason for the notation. So this is the conformal algebra, and this is R symmetry. And in addition to, so they all have some global symmetry, which is SON. And in addition to this, they have fermionic generators, and that's 4n real supercharges. It's 4n because we're just multiplying this n by this 4, and we get 4n. So the supercharges transform in the vector representation of SON. And there's half of them are like this, Q alpha I, where alpha goes from 1 to 2 and I goes from 1 to n. So alpha goes from 1 to 2 and I goes from 1 to n. And half of them are like this, S I alpha. And they're all Majorana spinners. The difference between Q's and S's is that the anti-commutator of 2 Q's is P. And so there's these supercharges, the Q squared to momentum. And the S is squared to special conformal generators. And I guess as far as conformal field theories are concerned, what's important about them is that the anti-commutator with the dilatation operator, so dq is 1/2 q, and ds is minus 1/2 s. So if we act with q on an operator, it raises the scaling dimension by 1/2, and if we act with s on an operator, it lowers the scaling dimension by 1/2. Okay. And now the operators transform in representations of this algebra. These representations, of course, can be decomposed into representations of the conformal algebra. So the operators transform in representations of OSP and 4, and each of these representations contains a finite number of conformal representations. So in a superconformal multiplet, there's a finite number of conformal primaries. There's one that's more special than the others, which is the superconformal primary, which has the property that when put at the origin, it's annihilated by S. The conformal primaries have the property that when put at the origin, they're annihilated by K. So in this multiplet, there's one operator that's annihilated by S. That's the superconformal primary. And then we can just act on it with Q's. So start with the superconformal primary. And we act with Q. And we get various operators, O prime, O double prime. Then we can act with Q again. And we get more complicated operators. Okay. So the lowest one would have scaling dimension delta. The next one delta plus 1/2. The next one delta plus 1, and so on. Some of the operators that we get are going to be conformal descendants. Some of them would be conformal primaries, but there's just a finite number of conformal primaries. Okay. So this is typically what the situation looks like. There are special representations for which some of the Q's annihilate the conformal primary. So there exist shorter representations for which some Q's annihilate superconformal primary. And it's these representations that one actually has more control over. So the number of supersymmetries in 3 dimensions can go from 1, 2, 3, 4, all the way up to 8. And the more supersymmetry there is, the more control there is over these short representations. Shorter is, so a generic representation starts with the superconformal primary, and then we act with any Q we want. We get some other operator, and so on, and we build the representation. There are shorter representations where some of the Q's annihilate the superconformal primary. So we have several operators in total in this multiplet. Okay. And an example of that is that of chiral multiplets. So let me just do a specific case where, so let me try to discuss n equal 2, where we can have chiral multiplets. They contain a complex scalar and a fermion. So these are complex. And these are short multiplets because this scalar is annihilated by half of the supercharges. Half of the Q's, sorry. Okay. So in n equal 2, the R symmetry is SO2R. In general, it's SON. In this case, it's SO2. And one can work out unitarity bounds just like for the for just conformal field theories. And one finds that if you want your operator, the superconformal primary, to be annihilated by half of the Q's, then its scaling dimension is fixed given its R charge, in terms of its R charge. So the property, the R charge meaning the charge under this SO2R. Okay? You can think of SO2 as U1. It just rotates the scalar by a phase. Just multiplies it by a phase. So in SCFTs, chiral primaries, scalars, have dimension equals to the R charge. Well, right. If they're anti-chiral, the R charge is negative, and the dimension is minus the R charge. And then I wanted to show you what happens if you try to bootstrap SCFTs, n equal 2 SCFTs, with a chiral scalar, well, chiral multiplet of R charge R. Again, this is equal to the scaling dimension of the scalar in that multiplet. The fermion would have the same, it would have a scaling dimension delta plus a half. So what do we need to do? Well, this scalar is complex, so we can write it as phi 1 plus I phi 2. And then look at the 4-point function, phi I, phi j, phi k, phi l. So this is, so look at this. And this is like the like theories with O2 symmetry. So we developed this whole formalism for theories with ON symmetry, so we can just apply it to this. What's different is that some of the, when we do the conformal block decomposition, some of the operators, some of the conformal primaries that appear in the conformal block decomposition are going to be related to one another by supersymmetry. So their OP coefficients would be related. Okay? So some OPE coefficients of conformal primaries are related by supersymmetry. So this gives the notion of superconformal blocks where we use those relations and we only sum over the superconformal primaries. But okay, this requires a lot of details. Let me just show you what happens if we try to put a bound on the lowest scalar that's a singlet under O2 as a function of delta phi. Okay, so upper bound on SO2 singlet scalar. Well, it sort of looks very similar to these other ones. So there's a kink somewhere. It sort of looks like this. There's actually two other features. There's some kink here and some other kink here. Those are, well, this one's not very well understood. This one is just, I think, a numerical artifact. But this one is interesting because this appears precisely when the dimension of the scalar is 2/3. Okay? And the theory that sits here is the n equal 2 superizing model. So the n equal 2 generalization of the Ising model. Okay? I can try to explain what this theory is. So it's a supersymmetric theory. It has scalars and fermions. And I can try to explain why the dimension or the R charge, so this is the dimension of this scalar phi is the same as its R charge. And I can try to explain why it's equal to 2/3. Okay? So what is the n equal 2 super Ising model? It is the theory of a free chiral multiplet. So one chiral multiplet. Well, it's not going to be free. One chiral multiplet, let's just call it phi. It has a scalar and a fermion. We can think of having a free chiral multiplet, and then we can add some interactions. And then in infrared, we flow to a conformal field theory. So the interactions are given by a superpotential term, which is W of phi is some coupling times phi cubed. In case you're not familiar with this, I can try to write down exactly what the Lagrangian is. So Lagrangian is this. We have a kinetic term for phi. Phi is complex. We have a kinetic term for chi. Chi is complex. And then we have a term that's a derivative of the superpotential as a function of little phi, quantity squared. And then we have another term that's the second derivative of the superpotential with respect to phi times chi chi. And then we have its complex conjugate, derivative of W bar with respect to phi bar, second derivative chi bar chi bar. So in this case, there's a quartic coupling for these scalars. This is g times phi absolute value to the fourth. G squared. And this term gives g phi chi chi, and this term gives g, if g is real, it gives g phi bar chi bar chi bar. So you can think of this model as this theory of one complex scalar, one complex fermion, with some interactions. And it flows in the infrared to a conformal fixed point, and it's actually a superconformal fixed point. It has supersymmetry, and actually the supersymmetry is preserved everywhere along the RG flow. Okay. So I can try to explain briefly how you can see that the R charge of phi, or its scaling dimension, is equal to 2/3. We just have to think about the symmetries that are preserved by this action. So recall that I said that these Q's have an index I and an index alpha. I goes from 1 to 2. They transform in the fundamental representation of SO2. So we can form these combinations. Q plus minus alpha, which is Q1 alpha, plus minus I Q2 alpha. And now Q plus has charge +1 and Q minus has charge -1. So Q alpha plus raises the R charge, if we think about it as a U1 charge, by 1 unit. And Q alpha minus lowers it by 1 unit. The condition for a chiral multiplet is that Q plus annihilates the scalar phi. So the only thing that can happen is to lower it. So I said before that for chiral multiplet, the superconformal primary is annihilated by some of the Q's. The precise condition is that for a chiral multiplet, Q plus annihilates the scalar. Okay? So, if phi has charge, R charge R, then chi has R charge. Well, chi is obtained by acting with Q minus on phi. Q minus has R charge minus 1, so it lowers the R charge by 1 unit. So chi has R charge minus 1, R minus 1. But then the question is, what is R? Well, R is such that this symmetry where phi, so the symmetry phi goes to e to the I alpha R times phi, and chi goes to e to the I alpha R minus 1 times phi, where alpha is just a transformation parameter. We want this to be a symmetry of this Lagrangian. Multiplication by a phase is certainly a symmetry of this term, is certainly a symmetry of this term, and of this term. The only questionable term is this one. And this is going to fix the value of R. So the phase that we get from phi is proportional to R. And the phase that we get from each chi is proportional to R minus 1. So we have 2 times R minus 1 is equal to 0. And then we can solve this equation for R. So we have 3R equal 2. So that means that R is equal to 2/3. And then the scaling dimension, as I said, for superconformal for chiral multiplets, the scaling dimension is equal to R charge, to the R charge. So that's the reason why the kink is at 2/3. Okay. Well, I'm not going to have time to explain how to calculate various things, but I do want to mention that in superconformal field theories, one can actually calculate the R charges of chiral operators using a procedure called F maximization. And from that, one can also extract correlation two-point functions of conserved currents. From the two-point functions of the conserved currents, one can obtain also, well, with some, maybe it's better to say that one can calculate the OPE coefficients with which the conserved currents appear, say, in the phi times phi bar OPE. Okay? Well, I'm obviously not going to have time to explain it. I wrote some notes on it, so I'll just post these. They're probably very, very rough. I should point you to some references. Anyway, but the main message is that in supersymmetric field theories, there are some quantities that we can actually calculate. And then we can, when we see a kink or something like this, we can check against these quantities that we calculated, see if it matches. So that would be a test. Or we can also use these quantities that we can calculate exactly as inputs for the conformal bootstrap, and then perhaps get better bounds. In using methods like this, it's possible to show that that generalizations, n equal 2 generalizations of the ON vector models. So by n equal 2, I mean with n equal 2 supersymmetry. Generalizations of the ON vector models. These must have some accidental or enhanced symmetries in the infrared by just combining all these techniques. Okay. Anyway, hopefully I gave you an idea of what CFTs in 3 dimensions look like. There are many things I didn't say, but, well, time is short.
More questions for Silviu?
Anyone?
So it's not like we can go home and reproduce those plots. You need a supercomputer.
It would be good to have at least several computers so that you have a cluster. But these plots, the ones for the fermions, those take a while to generate. This one or the one for the Ising model, those don't.
So I can do it on my laptop.
Yeah, I guess so. Yeah, it depends on, for the Ising model for sure, yeah. I mean, it's not going to be instantaneous. You're going to have to wait a while, but you know, you could.
Overnight?
Yeah, overnight you could do it.
Okay.
Yeah. Well, also it matters, like with what precision do you want to get it, like.
10%. How long would it take to get 10%?
Oh, that would be fast. That would be fast. I don't think that's overnight. It's less than that. Probably like half an hour on that order with SDPB. If you want to get like whatever they did, they got like 6 digits. Well, then you should not use your laptop. Yeah.
Looking into mixed operators, you won't get islands like this. Do you know how to get?
Well, no, it's possible. Like no one's looked at it yet in these models, or for the fermions. Yeah, so no one's done mixed correlators for the theories with fermions or for these theories.
What's the subtle?
Oh, for theories with fermions, as you saw, for just a single correlator, it looks extremely complicated. So doing mixed correlators would be even more complicated. We are working on doing mixed correlators between one fermion and one scalar. Hopefully, we'll be able to nail down this n=1 super Ising model more precisely. The GNY theory with n=1, which is supposed to have supersymmetry. For this one, I don't think anyone's done any mixed correlators. What would be good to do would be to do the mixed correlator between this external operator and which is chiral and this lowest scalar that appears that's R charge neutral, which is not chiral, which is part of a long multiplet. So for that, I think the first thing to understand would be the superconformal blocks. I don't think that's completely understood. Oh, sorry. So, okay, 2 scalars and 2. Right. Yeah, that's what I was saying about mixed correlators between scalars and fermions. That's what we're trying to do. Yeah. Right. But you can't just have 2 scalars and 2 fermions by itself. You have to combine it with 4 fermions and 4, a 4-point function of the fermions and a 4-point function of the scalars, and study that system of correlation functions. Yes.
So far, I think we've discussed.
Yeah.
Is it possible to discover new theories that would prove?
Well, there's certainly several kinks around that don't correspond to any known theories. For instance, the one over here is, I didn't draw it very well, but there is a kink over here, and this is one of them.
Is it believed to actually correspond to a real theory, or is it?
How would you know?
Yeah. It's not so clear. I think people, optimistic people believe that yes, it does correspond to a specific theory.
But so far there hasn't been like a clear discovery.
No, but it would be very hard to tell that you've really discovered a theory that's consistent. Yeah. Right. You can try to look at the various, try to look at scaling dimensions, try to look at the spectrum of operators. It would be good to have a guess as to what those theories are. Right. Yeah, even for the Grosvenor-Yukawa models, I think there are some additional kinks that might correspond to an additional fixed point. Actually, in the 4 minus epsilon expansion, you can see an additional fixed point. But that's there only, geez, I forget whether only for small values of n or for large values of n. Anyway, so in the d equal 3 plots, there is an additional kink, and maybe it corresponds to this additional fixed point, but it's not clear. So that would be another discovery of a theory where we might actually have an idea of what that fixed point might be. Yeah. By the central charge, you mean the normalization of the 2-point function of the stress tensor? Yes, that's right. That's one of the OPE coefficients. Actually, in the way I phrased it, the reason for that. So if you remember that what really multiplies the conformal block, G delta L, is this OPE coefficient, phi phi O, squared divided by the normalization of the 2-point function of that operator O. So if you look at the stress tensor, that means delta equals 3, L equals 2. This is the stress tensor, and this is T. What you mean, so the 2-point function of the stress tensor, T mu nu T rho sigma, would be proportional to CT. What you mean by CT is this coefficient provided that the OPE of phi phi t, this OPE coefficient is simple, provided that the stress tensor is canonically normalized. So when it acts on some field, it just some canonical expression multiplying that field. It's the same for all theories, right? So in that case, you would know this, and what multiplies the conformal block is essentially 1 over that CT. So for instance, if you put a bound on this OPE coefficient, I explained how to put upper bounds on these OPE coefficients. You'd find a lower bound on CT. Oh, geez, I don't remember the numbers, but people computed this. Right. This is one piece of information that we actually have about these theories. We know these central charges. Right. By the way, if you put a lower bound on CT for theories like the Ising model with just one, by looking at one 4-point function, you find that the Ising model minimizes the CT. But it's not clear whether that's a principle or it just so happens in that case that it minimizes CT.
Let's go look at the sun and bring coffee. Thanks, our speaker. Oh, that's nice. I learned a lot. I'll probably send you some stupid questions in the next couple of weeks.
Oh, yeah, sounds good.
Intergeneration.